I will give a short introduction before beginning.
Okay.
So, good evening, everyone, and welcome to the ninth alumni talk organized by Akash Ganga. Today we have with us Mihir Kulkarni. Mihir is a PhD student at Columbia University. His research focuses on population 3 stars and galaxy formation. He studies the formation of the first stars in the universe and various processes that delay their formation using numerical simulations. So, with this introduction, I would like to hand over to Mihir. Yeah.
Okay. Thank you so much to the organizers and for all of you to coming to my talk. It's great to see that IISER Astronomy Club is functioning well. I remember when I was at IISER, we had started an astronomy club, which I think had died just after a couple of months. So it's great to see this version, Akash Ganga, is functioning well for a very long period and has continued to organize series such as this. So I'm going to talk about my work during my PhD on numerical simulations of the first stars in the universe. So first question we can ask is, what do we mean by first stars and how can we define them? And there are various ways to define first stars, which are often also called as population 3 stars or POP3 stars. But a simplistic definition may be first stars are stars that are made from the primordial gas formed during Big Bang nucleosynthesis. That is, stars formed from only hydrogen and helium. So as we know, Big Bang formed hydrogen, helium, and their isotopes and traces of lithium, but no heavier elements. Whereas compared to that, the present day star formation has heavier elements like carbon, oxygen, nitrogen, silicon, iron, etc., which play an important role in gas cooling, resulting in very different properties. One question is, when and where do they form? So how early do the first stars form? How long after Big Bang do they form? Where do they form? Do they form in specific environment? Do they have to be in dark matter halos that follow certain criteria or not? And whether do they continue to form even to the present times? We can ask what are their properties that we expect, and if we expect those properties to be different from the present day stars. So far we have not seen any first stars directly, but from simulations we expect the first stars to be typically a lot more massive than the present day. So typically we expect them to be about 100 times more massive than Sun, but their mass can range anywhere from 10 to 1,000 solar masses. And there are various reasons for these differences. And we can ask, can we see them? Particularly with upcoming next generation telescopes such as James Webb Space Telescope, or in radio astronomy with Square Kilometre Array, can we see direct or indirect indications or signatures of these first stars? As these stars are expected to be a lot more massive, their supernova explosions are also expected to be very bright, and we expect to see some signatures from first stars in upcoming decades. So why do we care about population 3 stars? Why specifically about them? And why do we call them population 3 stars? So this is an somewhat older nomenclature, which started with calling the stars surrounding Sun and like Sun as population 1 stars. And metal poor stars in Milky Way were called as population 2 stars, that are older stars. And population 3 stars just refers to stars that are even older, that is the first generation of stars. And when these stars formed and exhausted fuel in them, they, depending on their mass, they exploded as supernova. And those supernova explosions started metal enrichment in the universe. So they formed heavier elements and they spread around with explosion from the supernovae. the subsequent generations of stars formed with metal enrichment, that is with carbon, nitrogen, oxygen, etc. And this led to very different properties for the second generation stars and so on. So it's important to understand properties of first stars, which started this whole process of metal enrichment and which goes on building up with successive generations of star formation and is needed, for example, for planet formation as well. These first stars also started emitting ionizing radiation. So they started ionizing the region around them, forming what are called as ionized bubbles. And with time, the ionized size of the ionized bubbles started to increase. And with first stars and first galaxies, more and more part of universe was ionized, up to a time when most of the intergalactic medium was ionized. So if we observe the intergalactic medium today, we find that most of it is ionized today. Only a very small fraction of it is in the neutral phase. And this phase transition is of very importance to cosmologists and astrophysicists. And population 3 stars are the stars that started this process. Again, the properties of first stars and metal enrichment from them affects the early galaxy formation. So properties of the first galaxies and second generation stars, etc., depend on properties of first stars, as well as we can constrain the nature of dark matter based on constraint that we can put on population 3 stars. So the standard model of cosmology is made up of, it's called lambda CDM, which has dark energy made up of cosmological constant and dark matter in the form of cold dark matter made up of so-called WIMP particles. But if the dark matter is made up of different particles, it may have different history with time, and that would also affect when population 3 stars would form. So if we can constrain from observations when pop 3 stars can form, we can also use that to constrain the nature of the dark matter. Okay. So just let's go with a little background of cosmology and try to understand when population 3 stars would form using simple qualitative physics arguments. So we know for nearly, is there a question? Okay. So we know for nearly 100 years now that universe is expanding, starting from Hubble's observation. And this can be written as the increasing distance between any 2 points, given as this function scale factor A of t, which increases with time. So universe is expanding with time, and that can also link with cosmological redshift as 1 plus z equal to 1 over a. So the scale factor is 1 today and was smaller at earlier times. And so correspondingly, the cosmological redshift corresponds to 0 today. And for distant objects or for earlier times, the redshift is higher and higher. And as universe expands, the matter density decreases because of expansion. It decreases as a to the minus 3. And this also results in the temperature of the universe decreasing with time because of expansion. So this is true for temperature of universe or temperature of the cosmic microwave background that we observe. So this leads us to conclusion that the early universe was hot and dense. So this is a schematic diagram of the cosmic history of the universe. So after Big Bang, universe was very hot, and up to nearly 400,000 years after Big Bang, universe was ionized. That is, protons and electrons were separate and they were coupled with radiation. So light was constantly scattered off electrons and protons. When nearly 400,000 years after Big Bang, universe cooled for the first time, that stable neutral atoms could form. So proton and electrons could recombine to form neutral hydrogen atoms called as recombination. And this decoupled matter, or that is baryons with radiation. And radiation emitted at that time can be seen even today as cosmic microwave background radiation. And after this period, there was no new source of light, which is why this era is also called dark ages. That is, the only light there was what was emitted from recombination era. But this continued for some time when we started forming the first stars, which we are interested in. So we started to form first stars, and with time, more and more clusters of first stars or first galaxies, and they started reionizing the universe. And by nearly redshift of 6, the universe was completely reionized, and we end up here today. Okay, so from the cosmic microwave background, about 400,000 years after Big Bang, we can see how the universe was. And this is the map of CMB from Planck 2018. And universe was homogeneous to a large degree, with tiny inhomogeneities present when we look at different angles. So CMB corresponds today to temperature of 2.73 kelvins, with some parts being slightly hotter, shown in red, and some parts being slightly colder, shown in blue color here. And these tiny inhomogeneities at the epoch of recombination grew with time because of gravitational effects, and led to the structure formation of galaxies, galaxy clusters, etc., that we see today. So this can be understood using numerical simulations of dark matter. So as we know, dark matter is a lot more abundant than baryons and does not interact with radiation. So the structure formation is primarily governed by gravitational effects of dark matter. And this can be seen from this simulation of dark matter only done by Volker Springel. And this is dark matter only evolving with redshift. So you can see this is at redshift 30 now. And with time, we form denser and denser dark matter collapsed object. So this is called hierarchical structure formation. So that is, you form smaller halos first, that is collapsed dark matter objects, and with time they accrete more and more mass, or dark matter halos merge with each other to form more and more massive structure. So you start from mini halos or low mass halos in dark matter structure, and with time you form more and more massive halos, more and more massive galaxies and galaxy cluster, as you can see in the simulation. These halos merging to form more massive halos. And baryons more or less follow the gravitational potential well of this dark matter, as dark matter is a lot more abundant. So question we can ask is, in which halos do we form first stars? When do we form them for the first time? And can we understand that using simple physics? Okay, so let's look at what do we need for forming first stars. So primordial chemistry, that is formed in Big Bang, has 75% hydrogen by mass, 25% helium by mass, and traces of lithium. So there was some beryllium-7 also formed during Big Bang, but which comes back to lithium again. So there are no heavy elements formed during Big Bang. And if we want to cool a gas, what are the effective pathways? So for example, all of us know about transition lines of hydrogen atom. So we have n equal to 1 to n equal to 2, which is the Lyman alpha transition, which corresponds to nearly 10 electron volts. So suppose your gas is at temperature of 7,000 Kelvin, and most of the hydrogen is sitting in the ground state. In that scenario, it cannot really cool because for gas to cool, it has to be collisionally excited to Lyman alpha transition or any other higher levels, and then it can emit radiation back and come to ground state, and in that way it can cool radiatively. But for that to happen, the gas needs to have at least a temperature of 10 to the 4 Kelvin. So if the gas does not have that much temperature, it would just stay in the ground state and would stay at that same temperature and would not be able to cool. However, there can be some molecular hydrogen formation as well. So after recombination, even though universe became more or less neutral, there was some electron fraction that remained after that, and that can combine with hydrogen to form H- ion, which can form molecular hydrogen. And molecular hydrogen is not a very good coolant because of its symmetry, but the rotational and vibrational transitions of molecular hydrogen can cool the gas to about 200 to 500 Kelvin. And it's important to know that if we do not have sufficient molecular hydrogen, or whether the gas does not have this temperature, the gas cannot cool. And we need gas to be cool so that it can become dense enough to lead to formation of a star. So it's important to know that gas needs to be warm, that it needs to have at least certain temperature for it to be able to cool. Okay, and this can again be shown in terms of what is called as cooling function. So the y-axis here is cooling rate for a given density of atomic hydrogen and molecular hydrogen as a function of gas temperature. And if you only consider the red line here, this is in absence of molecular hydrogen, and we can see that the cooling rate falls off very rapidly below 10 to the 4 Kelvin, as we expect. So if we don't have any molecular hydrogen, you need at least 10 to the 4 Kelvin temperature for gas to cool. And this peak in the cooling function we see corresponds to primarily Lyman alpha cooling of hydrogen. And the second peak corresponds to cooling because of helium. However, if we do have molecular hydrogen, as is shown in this red dashed lines, the gas can cool to temperatures below even 1000 Kelvin, up to few hundred Kelvin. And this is important for formation of stars. Okay, so let's propose a very simple analytic models for what do we need for to form the first stars in these halos. So as some of you may know from the virial theorem, if there is a stable kinetic system with time, its potential energy is -2 times the average kinetic energy. So if a dark matter halo has collapsed and has become stable with time, there's a relation between how its velocity distribution and its potential energy. And the gas inside the dark matter halo is also heated because of shocks to what we can define as the virial temperature because of this virialization. So the gas temperature is nearly same as the virial temperature. And the virial temperature can just be defined from the virial theorem as corresponding to the gravitational potential energy, that is G virial mass times mass of the proton, or the reduced mass of gas that we are talking about, divided by virial radius of the dark matter halo. And that gives us a typical temperature of gas that would be present in a halo of given mass. And with time, these dark matter halos accrete more and more mass with time. So their virial mass increases with time, and so does their virial temperature. So we can define.
Sorry to disturb. Can you clarify on the virial radius once again? What exactly is the virial radius of a dark matter halo?
Right. Good. So virial radius is the radius over which this dark matter halo is bound. So there are various ways to typically identify this, but one most common way is a virial radius is the radius inside which the average density of the dark matter halo is 200 times the background density of the universe. So universe has some background density at a given time or given redshift. And so virial radius is just the radius inside which the average density is 200 times more. And there are various calculations or arguments you can make for that specific number, but that's the typically used definition.
So it's sort of an arbitrary bound, right? And it's the dark matter is sort of continuous, like a gradient.
Right. It is continuous. Yes.
Okay.
Yes. But
Thanks.
it is not exactly arbitrary. So there are some physical arguments for it. But yes. Yeah.
Okay.
Yeah. So we can define a criterion for collapse, that is to form stars, as to have cooling time for the gas to be shorter than the Hubble time or dynamical time for gas to collapse. So we can define the cooling time of gas as for any region as its thermal energy divided by cooling rate. That is, if we ignore all other processes and if we assume there's only cooling, what's the typical time scale for gas to cool? And this, the energy can be just thermal energy can be written as 3/2 nkt, and the cooling rate for gas depends on the atomic hydrogen number density, molecular hydrogen number density, and the cooling function as a function of temperature that I just showed you here. So it depends on how the cooling function changes as function of temperature as well as what are the densities. And the Hubble time is just inverse of the Hubble parameter. So remember again that even though Hubble parameter is typically mentioned in units of kilometers per second per megaparsec, it just has dimensions of 1/time. So Hubble time is just inverse of the Hubble parameter, and it's a relevant time scale for the collapse. Or you can also define a time scale for gravitational collapse for a given density, which is very similar to this Hubble time. And we can define criteria for collapse as that the cooling time should be shorter than the Hubble time. So the gas should be able to cool efficiently and cool to very high densities, and then it can form stars. And we can make some simple models for how, for example, how does the gas density change as a function of virial mass of the dark matter halo. As I mentioned, we can assume the gas temperature to be equivalent to the virial temperature of dark matter halo, and so on. And using that, we can define what is called as critical mass. That is the minimum halo mass that is needed by dark matter halos to form first stars. That is, if a halo is more massive than critical mass, it would have sufficient temperature and sufficient densities so that the cooling time would be short enough and it would be able to form stars. So if you have a halo of mass, say 10 to the 4 solar masses, the temperature and gas densities would not be sufficient for it to cool within a Hubble time, and it would not form stars. Okay? So this is the typical scenario from a simple analytic models. And the next question we can ask is it same in different parts of the universe? Does it change with time? And does it depend on environment? And does it depend on feedback processes?
Mihir, there are a couple questions in the chat.
Okay.
Can you see them?
Yes. Okay. Why wasn't the universe perfectly homogeneous? One answer we can say from what we know is we can observe how universe was 400,000 years after Big Bang, that is in the cosmic microwave background, and we do see it to be inhomogeneous. So we see tiny inhomogeneities present at that time, and there are various arguments for why that was the case. And one popular argument is during the inflation, you get these inhomogeneities from the quantum fluctuations in the vacuum. Electrostatic potential energy for the virial theorem. No, I mean, it's if you have mostly neutral gas, yeah, it's mostly gravitational potential energy that we are talking about here. Because remember again in cosmology, gravitation is the large scale force primarily. Okay.
Mihir, sorry, can you go back to the previous slide?
Yes. Yeah.
Here, if the cooling time is less than Hubble time, then this is a criterion for collapse. So if you take the current scenario, so the inverse of the Hubble constant right now gives an estimate for the age of the universe, right?
Right.
So in that case, the cooling time will definitely be less than the Hubble time. So what is the implication of that in the current scenario?
Right.
In the modern.
Yes, that's a good question, which effectively means that if you have a massive enough halo present today, it would form stars. So this
Okay,
is
so there's an additional mass criteria also.
So this is assuming a very simple prescription. So for example, today we also have ionizing radiation from other stars or nearby galaxies, which is not considered here, which would be heating the gas. So this is a very simple analytic model where you don't have any ionizing radiation or any other source of heating. So as there is cooling from molecular hydrogen, there can also be sources of heating, such as ionizing radiation, as I mentioned. And in that scenario, you need to account for the heating rate as well, which is present today. So you cannot blindly use this procedure today. But to give you a simple answer, if you find a patch of universe which does not have any heating, then nearly any halo would form stars.
Okay, thank you.
Okay. Yeah, that was a good question. Okay, so one process that can delay the formation of first stars is what is called as Lyman-Werner radiation. And as I mentioned, molecular hydrogen is necessary for cooling of the gas in these small mini halos. And as you start to form first stars in one part of the universe, they start to emit radiation, and they also start to emit these Lyman-Werner photons, which have energy between 11.2 to 13.6 electron volts, and they can dissociate molecular hydrogen. So the scenario is you form first stars in some part of the universe, they start emitting this Lyman-Werner radiation, they start to dissociate molecular hydrogen in the region surrounding them. And as you form more and more stars, they start to build up a background radiation of Lyman-Werner photons. So if you are in the region of high Lyman-Werner radiation, molecular hydrogen is dissociated more and more. And if it's dissociated, star formation can be suppressed. Because if you don't have molecular hydrogen, the gas needs to be very hot and halo needs to be a lot more massive. So this can delay the formation of first stars. However, massive halos can have higher gas densities, and they can self-shield themselves from this Lyman-Werner radiation and still form some molecular hydrogen and cool. So therefore, if there is a Lyman-Werner radiation, POP3 stars form only in massive halos, but they cannot form in low mass halos. So in turn, what is happening is the critical mass that I described just here is increasing in presence of Lyman-Werner radiation. Okay, and depending on if it's very strong Lyman-Werner radiation, the critical mass, we expect the critical mass to increase to even higher values. Okay, so this is one effect that can delay the formation of first stars. And the other effect.
Yeah. Excuse me. I have a question. I'm sorry if I missed it, but what is the origin of the Lyman-Werner radiation?
Oh, it's just the stars. So this is what is called as feedback processes, feedback effects. So there are different.
Sorry, which star produces the Lyman-Werner radiations?
The first stars. So there's no only one first star in the universe, right? So there are different halos, and in them you form these so-called first stars or population 3 stars at different times. So suppose you form population 3 stars in one halo, and those stars start to emit Lyman-Werner radiation because as they're bright, they emit light in all wavelengths, more or less, but they also emit light in these Lyman-Werner bands. So a halo which is next to the halo that we are considering, neighboring halo, now is exposed with this Lyman-Werner radiation, and POP3 star formation in that nearby halo is now delayed because of this Lyman-Werner radiation. Okay, so this is called as negative feedback. So you form first stars, population 3 stars in some halos, and that formation delays further population 3 star formation in nearby halos. Okay, so this is negative feedback. You start something and that process itself hinders more formation of the same process. Okay. Okay, so I'll continue, but if there are more questions, I'm happy to answer this again.
Yeah, I have a question.
Sir.
Yeah. Yes, if the energy is higher than 13.6 electron volts, not only it can dissociate, it can also ionize the atomic hydrogen. So that is entirely correct. But yeah, if it's higher than 13.6, it's going to ionize the neutral hydrogen, and so it's not able to pass any further because what is called as optical depth of atomic hydrogen is very high, whereas molecular hydrogen is present in very small quantities. So you are absolutely correct that ionizing radiation also has an effect, but molecular hydrogen is necessary for cooling, so we focus more on that, and it governs what we are interested in to a higher degree.
Okay.
And one other process that can delay the formation of first stars is what is called as baryon dark matter streaming velocity. So consider time just before recombination. That is, baryons or normal matter is ionized. So there are protons, electrons, which are coupled with radiation. So light is being constantly scattered off the electrons and protons. So this is called as coupling. So baryons and radiations are coupled with each other, whereas dark matter does not interact with radiation. So dark matter evolves under its own gravity and starts to build up gravitational potential wells, shown here in gray particles, whereas the baryons evolution is mostly determined by what is happening with the radiation, and they do not fall in the potential wells of dark matter. This is just before recombination. So the effect of this is in some part of the universe, because what is happening, you may be in a region where dark matter and baryons are moving in same directions with more or less same velocities, whereas in some other parts of the universe, you may have a case where baryons and dark matter are moving with respect to one another. And this is just the effect of the fact that baryons were coupled with radiation and dark matter was not. And this results in what is called a streaming velocity between baryons and dark matter. So in some parts of the universe, baryons, that is normal matter gas, was running away from dark matter with certain velocity. And this is a phenomenon which you just get from if you solve the cosmological perturbation theory, but was first pointed out in 2010. And this net streaming velocity is coherent over fairly large distances. And this follows Maxwell-Boltzmann distribution with RMS root mean square velocity of nearly 30 kilometers per second. And this streaming velocity decreases with time. So it's not important today. So if you look about it for in any papers about, say, star formation in Milky Way, you won't hear about it because it's not important, because it becomes very small. But when we are talking about high redshift phenomenon, such as formation of first stars, it is significantly important. So again, different patches of universe can have different streaming velocity between baryons and dark matter. So suppose you are in a patch of the universe where baryons or gas is running away from dark matter. So in that scenarios, the halos are gas poor because just the baryons are running away from dark matter, and halos need to be more massive and have stronger gravitational pull to pull those baryons back and have sufficient gas densities, which would mean that to form stars, halos need to be more massive to have stronger potential wells to form first stars. So in this scenario, we also expect the critical mass, that is the minimum halo mass you need to form first stars, to increase. Okay, so it depends on what is the streaming velocity in your environment. So these are the two important effects that can increase the critical mass of the halos. So where and when population 3 stars form. Okay, and just to give you one example, so this is just initial conditions showing gas density overplotted with gas velocity arrows, case without streaming and case with streaming velocity. And in the left case, you see just that the velocity is following the density structures that we see. For example, the velocity is going to the dense region here, whereas in this case, we have added a streaming velocity in this one direction, x-axis. And on top of this added streaming velocity, this also erases some small scale structure, which can delay, which is going to delay formation of first stars. Okay.
I have a question, if you don't mind.
Yes. Yeah.
So at what redshift does the Lyman-Werner metagalactic background start, roughly?
Right. So it starts when you start to form first stars. So it can vary with time, but yeah, roughly around, we expect first stars to start form at redshift between 30 to 15 or so. So it starts to build up with time. So it changes with time, as well as it varies from region to region as well. But yeah, I would say it starts around redshift 30 to 25 or so. Yeah.
And is this with the evolution, as more and more stars form, does the Lyman-Werner, I mean, if you look at the distribution function of the energies, does it get steeper or does it get flatter towards, say, lower redshifts?
That's a good question. So it also depends on what is the spectrum of the stars that are emitting it and what's their temperature is and what their numbers are. But we can assume for this energy range we are talking about, we can, for now, we can ignore its energy dependence and we can just take it to be flat.
Okay, thank you.
Yeah. Okay, and to do, we can identify the critical mass for population 3 stars using numerical simulations. And what we typically do for solving cosmological numerical simulations is we treat gas as a fluid, and we can solve, to evolve it in time, we can solve what are called Euler equations, that are fluid equations. So the first equation is generalized mass conservation law. The second equation is generalized momentum conservation law, and the third equation, E here, is thermal energy density of the gas. And in here, we can also include terms from the cooling of the molecular hydrogen and neutral hydrogen, as I mentioned, as well as any heating processes that are present. And we need to modify these equations slightly to account for the expanding universe that would also decrease the densities with time. And we use an adaptive mesh refinement simulation code called ENSO. And what it does is, instead of using very high resolution everywhere in our simulation box, it refines our grid to very high resolution only in the regions where we need it. So we have a box, and depending on the gas densities and whatever criteria we can define, we can form a grid, and we can only resolve that part to split the grid that we're using and run it with higher and higher resolution. So this is called adaptive mesh refinement. So one advantage of this is we can run very high resolution simulation that is focusing on star formation, while also including sufficiently large cosmological boxes to to include the effects from cosmology. Okay, so this can, with adaptive mesh refinement, we can study multiple orders of magnitudes without them being too computationally expensive. And this is just to show. Yeah.
Sorry. Can you explain what exactly is the grid? I'm sorry if I didn't get what the grid means.
Yes. Okay. So you need to solve this equation. So you can say you have a cell in your simulation, and each cell would have all the physical quantities associated with it. So for example, each cell would have certain density, certain pressure, certain temperature associated with it, and you can just evolve it with time. So suppose you don't have any this fancy smaller grid. So suppose you have a uniform grid. That means that you have cells of equal size, and each cell has all the physical quantities associated with it. And you just evolve all those quantities with time, solving these equations of fluid dynamics. Okay, so you are approximating, so you are not solving it for, say, each individual particle or each individual molecule. So you are treating gas as an ideal fluid, and you are just seeing how these properties of this fluid evolve with time. And the results would be more and more accurate if you use better and better resolution. Okay.
So it's a 3D grid then, right?
Yes, these are 3D simulations. Yeah, this is just, I'm just showing the 2D slides, but yeah, these are 3D. So it's a 3D box. Yeah.
Thanks.
Yeah. So just to show you one example of this. So this is showing a slice of same halo without any Lyman-Werner background radiation, and the same halo in presence of Lyman-Werner background radiation. And this is using the same scales, all the same scales, and we can see that there is difference in the gas density. That is, in absence of Lyman-Werner radiation, gas reaches much higher densities in the center. That is absence in presence of Lyman-Werner radiation. You can also see the difference for the molecular hydrogen fraction. That is, the molecular hydrogen fraction, in this case, without any Lyman-Werner background radiation, is close to 10 to the minus 3. That is 0.1% of all the gas is in molecular hydrogen, whereas Lyman-Werner background radiation is dissociating all the molecular hydrogen, and the molecular hydrogen here fraction is 10 to the minus 8 or so. And only the central dense region is able to have molecular hydrogen fraction of 10 to the minus 4 or so. So this is just showing if you include Lyman-Werner radiation, that dissociates molecular hydrogen that is needed for cooling, which results in you not getting dense enough structures. Yeah, and this can also be seen in temperatures. For example, here we can see the central region here is able to cool to few hundred Kelvin, which is absent here. So if you don't have molecular hydrogen, you cannot cool to few hundred Kelvin temperature. So this is just one halo from our simulations. Okay, so one of my recent project was to understand how identify critical mass, how it depends on redshift as well as Lyman-Werner radiation and streaming velocities using a simulation suite of high-resolution cosmological simulations, and to see how well it compares with simple analytic models, and do we need to do improve those analytical models and so on. So we included 4 different Lyman-Werner backgrounds, going from no Lyman-Werner backgrounds in units of this J21, which is typical value, to including various Lyman-Werner backgrounds, as well as including 3 streaming velocity cases. And we can, so this is just a way to identify the critical mass. So this is showing at a given redshift, the x-axis shows the halo mass, and the red line here shows the fraction of halos at that given mass that have cold and dense gas that would form first stars. And I mentioned that halos that are more massive than critical mass form first stars, and halos that are that have mass lower than that do not form. But we can see that it's not a sharp transition. but instead there's a significant scatter. That is, there are at critical mass, we define it to be a mass where 50% of the halos have cold and dense gas and form first stars. But it's important to keep it in mind that this is not a step function, and when population 3 stars form in a given halo depends a lot on the history of the halo, its merger history, as well as its spin, etc. So just to show you some results, so this is showing how critical mass changes as function of redshift. So the blue line here shows the default case, that is, does not include any Lyman-Werner radiation. And what we find is the critical mass is few times 10 to the 5 solar masses, and it also changes with redshift, as was predicted in analytic models, but was not seen in simulations with large number of dark matter halos. And we also find that when we increase background Lyman-Werner radiation, the critical mass increases. That is, for very strong Lyman-Werner radiation, the critical mass can be increased by up to 2 orders of magnitude. That is, if you are in the region of high Lyman-Werner radiation, halos form, first stars form in only very massive halos. And this plot shows a similar result for the effect of streaming velocity that I mentioned. So again, the blue line is the case without any streaming velocity, and the green and red lines show what would be the critical mass when you are in region of high streaming velocity. And as we expect, if you are in region of high streaming velocity, the critical mass is a lot higher. We showed this from our simulations. And for the typical values of Lyman-Werner radiation and streaming velocity, we find that streaming velocity is important, more important. Okay, so for time being, I'll skip this slide, but if people have questions about this, I'll come back to this. So just to summarize this point, I mentioned what the critical mass for population 3 stars.
Sir, I had a doubt in the last to last slide.
This one? Yeah.
Yeah, so here we are considering the mass. We are directly considering the critical mass while star formation, right?
Yes.
But if the mass is extremely scattered out, i.e. low density, how will the star form? Like, shouldn't we instead look at the density of the?
Right. Yes. It's a good question. So when the star form depends on what the gas density is, but the question is, why are we using linking it to the halo mass? That's a very good question. I'll come to that in just a minute. Yeah, it's a very good question. Yes. So we found how critical mass changes as function of redshift in absence of Lyman-Werner radiation and streaming velocity. And we also found that critical mass increases with Lyman-Werner radiation as well as streaming velocity. And we provide a fit for the critical mass as function of Lyman-Werner radiation, streaming velocity, and redshift, which can be used by semi-analytic models of early galaxy formation. And let me explain what I mean by that. So for example, the simulations I showed where we follow the evolution of gas to very high densities to see when the stars would form are very computationally expensive. So you can do those for small box, which are not representative sample, for example. But what is more often done is we just do simulations of dark matter, which only the only force of relevance is gravitational force. And so those dark matter only simulations are much cheaper, a lot less computationally expensive. So if we have a dark matter only simulation, in those simulations we can see how a halo is growing with time, dark matter halos, and we can use this critical mass to link to the locations of dark matter halos to the formation of first stars. So, and those dark matter only simulations can be done with much larger boxes and can include a lot of physics. So point of the work that I just explained is what is sometimes called as subgrid physics as well. So you do study a specific phenomenon using high resolution zoom in simulations and use results from them in cheaper simulations which can probe a much larger volume. So point of this is if we are able to link where and when first stars form to the properties of dark matter halos, then we are able to use it with computationally inexpensive dark matter only simulations. And the variations because of this streaming velocity that I mentioned can have effect on 21 centimeter signal from the neutral hydrogen, which is expected to probe the processes of reionization. And this streaming velocity can also cause variation in when the reionization occurs. So I can drop few points which I can talk about more if you have any questions. So one point is how late can POP3 stars form? So I mentioned the simple processes where they form at redshift 30 to 15. But what happens when the molecular Lyman-Werner radiation is very strong? How late can they form? Can POP3 stars form today? How does the fragmentation of gas occurs? So I mentioned in the beginning that the typical mass of POP3 stars is much higher than the present day star. Why is it, and how can we understand using physics? And what are some of the effects of the nature of the dark matter? So I in particularly worked on what is called as fuzzy dark matter, which is made up of ultralight particles, and its quantum mechanical effects are fascinating. So if you have questions about that, I can also talk about that. But I'll just end by saying what I did through IISER. So during my time so I was at IISER from 2010 to 2015. And I took mostly physics courses and few maths courses when I was in IISER. And my first experience with astronomy was when I attended radio astronomy winter school in December of 2011 in my second year. But I didn't do any research in astronomy until my third year project. So for example, my second year summer project was in like a reading project in linguistics with KP Mohanan. But my first astronomy research was at NCRA in third year summer, where I used wavelet transformations to identify diffuse radio emission with Neeraj Mohan Ramanujan. So just to give you one example of that, you have a picture of Andromeda galaxy. You can decompose it to various scales, going from small scales to very large scales. And looking at the decomposition at very large scales, you can use them to identify diffuse large-scale emission in radio surveys. So this was my first astronomy research project, so using image processing to identify those structures. And in the next summer after that, I again worked at NCRA with Neeraj again on commissioning of 15-meter radio telescope at NCRA. So you may have, if you have been to NCRA, you may have seen this 15-meter radio telescope, which is there in the backyard of NCRA. And this is supposed to be used for teaching primarily, but it was a newly built telescope, and I worked on commissioning of it, that is finding out what is the noise, what is the beam width of this radio telescope, what is the error or the offset for this telescope. So this was a lot of instrumentation and learning how a radio telescope works from scratch. And it was a lot of fun to be able to just move the radio telescope to whichever direction I want and observe bright sources. And I did my master's thesis with, again at NCRA with Tirthankar Roy Chaudhary on theoretical cosmology. So studying distribution of neutral hydrogen with time and studying reionization. But after that, since 2015, I have been a graduate student at Columbia University, and I have been working on what is called as fuzzy dark matter, as well as primarily now on the formation of first stars. So I'll stop here and take any questions about any of the topics I've mentioned or anything you have. Thank you.
Sir, the mass density one.
Yes. Okay. Yes, yeah, that's a very good question for can ordinary matter alone aggregate to form stars, or is it too sparse to aggregate? So I'm not sure what you mean by ordinary matter. So when you form stars, it is from ordinary matter, that is baryons that we know about. If you are, yeah, baryonic matter. So stars form from baryonic matter, but its evolution is determined to a large extent by the structure of dark matter halos. And the reason for that is dark matter is just a lot more abundant. So the evolution of baryons is to a large extent determined by the gravitational potential wells created by dark matter halos. Because if you somehow manage to be in a region where there's no dark matter, but there is baryons, the gravitational pull of the baryons in most cases would not be strong enough to form stars. Yes, and then the one question is, can population 3 stars be used to check the validity of cold dark matter versus, say, warm dark matter? That's a very good question. So some of you may know warm dark matter is an proposed alternative theory to cold dark matter, or a similar theory is called fuzzy dark matter. And these theories are proposed to solve some of the small scale problems of the lambda CDM. So the lambda CDM, that is the standard model of cosmology, explains what we observe on large scales very well. So it explains CMB, it explains, say, number of galaxy clusters, cluster abundances, etc. very well, but it starts to break a little bit when you go to small scales, that is the scales of galaxies. For example, one problem is what is called as missing satellites problem. That is, the number of satellite galaxies predicted for a Milky Way like galaxies is a lot higher in CDM than what we observe from observations of dwarf galaxies. So warm dark matter is one such candidate, and another such candidate is what is called as fuzzy dark matter. And one important difference is in those alternate models, the minimum halo mass of dark matter is something like 10 to the 8 solar masses. So all the mini halos that I talked about at very high redshift would not exist in those scenarios. And population 3 stars, their formation would be delayed to much later times. So it is indeed true that they can be used to put constraint on the formation of stars, definitely. Yeah, so if you are interested, I can also show something about fuzzy dark matter, which is, I think, a fascinating theory, alternative theory to dark matter.
Yeah, please, that would be great if like you have time.
Okay. Do you see this? Yeah. So this fuzzy dark matter is proposed alternate theory to cold dark matter, and it is made up of ultralight axions. So their typical mass is of the order of 10 to the minus 22 electron volts. So let that sink in for a bit. So when we talk about low mass particles such as electron, the mass of the electron is nearly half MeV. Mass of proton, when we talk about, it's close to a GeV. So these are ultralight axions. So their mass is extremely low. And one consequence of this is the de Broglie wavelength of this particle is of the order of 1 kiloparsec. That is the size of core of dwarf galaxies. So one effect of this is you cannot form, you cannot restrict it to be for a size smaller than, say, 1 kiloparsec. That is its de Broglie wavelength. So that puts a limit on what's the minimum halo mass that can exist in this fuzzy dark matter cosmology, and it's proposed as one of the ways to solve the small scale problems I mentioned for the fuzzy for the standard cold dark matter. And this may be a one of the best ways to constrain studying first stars and first galaxies would be best way to constrain the mass of this fuzzy dark matter. So for example, this is showing a density slice passing through a fuzzy dark matter halo, and we can see this interference pattern that we can see that we are all familiar with quantum mechanical effects, and these interference effects would be present on scales of few kiloparsec because of their such low mass. So I've been working on when would population 3 stars form in such alternative to the standard cold dark matter.
Is there some alternate way to constrain the first populations? The first stars, so that we can check the cosmological models as well.
Right. Yes. So the way it would work is if we are able to put any constraints on, say, first stars or first galaxies from observations, then we can use those observations to put constraint on the properties of this fuzzy dark matter. So for example, fuzzy dark matter restricts how many massive galaxies there would be at, say, redshift 10, because all structure formation is delayed in fuzzy dark matter scenarios. So suppose we observe many galaxies at redshift 10, we can use that to constrain what is the mass of fuzzy dark matter. Because if the fuzzy dark matter is more and more massive, it becomes more and more similar to standard cold dark matter, as you can expect. And as the mass is lower and lower, its quantum mechanical effect become more and more prominent. So it won't be possible to constrain the fuzzy dark matter right now from what we observe, but with the observations that are possible from the next decade, we would definitely be able to constrain these properties of fuzzy dark matter.
Thank you.
What is the resolution for the ENSO simulations, for the FDM?
These FDM simulations?
Mass resolution.
This doesn't do mass resolution. So what we do is only spatial resolution. Okay. So the way it works in ENSO is
grid-based.
You have a spatial, it's a grid-based code. So if you reach high enough densities, we resolve it to smaller and smaller scales, but we do not have that yet for the fuzzy dark matter. So I would say resolution for this is few hundred parsec. So this is still not very high resolution, but the important criteria for solving fuzzy dark matter simulation is you need to resolve the de Broglie wavelength of the dark matter, which is of the order of kiloparsec. So our spatial resolution is smaller than that.
And a follow-up to that, to account for the uncertainty principle, do you set a initial cutoff in your initial power spectrum?
That's right. Yes. We do need to set that up, but the way this simulation is essentially run is by solving Schrodinger and Poisson equation. That is, you have a universal wave function for the entire simulation box, and the density at any point is just the modulus square of the wave function at any location. And in the Schrodinger equation, we include the gravitational potential of the dark matter using the Poisson equation. So the evolution of this particular simulation is not done like normal dark matter only simulation, where we are just taking bunch of particles and evolving them under gravity. We are actually accounting for all the quantum effects by solving the Schrodinger equation on the entire box.
I see. Okay. Thank you.
My 5th year experience at IISER Pune. Yes, so I for 2 summers I worked at NCRA on very different uh, projects, but they were mostly related to radio astronomy. And I also wanted to try something different, something more theoretical. So in my last semester of fourth year, so eighth semester, I did uh, a semester project with my advisor Tirthankar Roy Chaudhary to explore what different things can you do in astronomy. So I did that, and so that was like mostly familiarizing with cosmological simulation, learning some basic cosmology theory, etc. And I enjoyed that, so I continued working with him for my fifth year project. So yeah, I understand it's not always easy to identify whom to work with for your fifth year project, because you're going to spend an entire year, and who knows, you may not end up liking that specific project, or you may not end up liking the advisor. So I would say, if it's possible, it helps greatly if you have worked with that advisor for some time, and you know how it is to work with that specific advisor. In that case, it may be a lot easier. At least it was in my case. Yes. Yes. So one idea that I had in my mind while deciding for a PhD program, that it should have what is called as grad school in astronomy. So I preferred programs that are in astronomy department rather than a physics department. And the reason for that is, in IISER, we had only one astronomy course, which had everything, but which didn't go into a lot more detail. So the only things in astronomy I knew about was part of some cosmology and maybe some basics of radio astronomy. And I, for example, didn't know much about, say, star formation or galaxy dynamics, etc. So I wanted to go to a program where I would take graduate courses in various topics of astronomy. And one good thing about the PhD program at Columbia Astronomy is, for the first 2 years, we have to take 8 grad courses, and 5 of them are compulsory for everyone, which include like cosmology, radiative processes, star formation, galactic dynamics, and then there are some optional courses like fluid dynamics or astrophysical instabilities, or seminar courses focusing on specific courses. And also at Columbia, I think a good thing is you do not start working with an advisor right away, whereas we are forced to work with 2 different advisors for our first year and second year project. So we are encouraged to work with 2 different advisors, and possibly on very different topics before deciding on a thesis project. So my first year, I worked with Jerry Oestreicher on fuzzy dark matter, and so identifying halo mass function from analytic models, how to calculate that. And for my second year project, I started with my current advisor, Greg Bryan, on simulations of first stars. And for my thesis, I continued essentially my second year project, and I've been working with him. But for various students, some of them go back to working with their first year advisor, or some of them decide that they didn't like either of their first 2 advisors and end up working with a third advisor. But for me, I thought it was good to explore somewhat, even though they were mostly in cosmology, various topics, and work with different advisors, because I felt like I didn't know what all things are there to do in astronomy. I had done like 1 or 2 projects on a specific part of astronomy, and I wanted to know more about what all things are there before deciding that I want to spend few years on working on this specific subtopic. So I would say it worked out well for me, but different programs have different strategies, and some programs allow you to do a rotation with shorter projects for like 3 months or 6 months before deciding an advisor, whereas in some departments you just start right away working on a specific project. So it may work differently for different people depending on how much you know about what you are currently working on, and how much you know about that topic and how much you want to continue working on that specific topic. One other different thing is in IISER, the life is constrained by coursework to a large degree, and which was somewhat similar for the first 2 years of PhD, but not later. And this can be somewhat disorienting to not have any structure that is defined by coursework, and you need to decide your own structure, which was somewhat true for the 5th year thesis project as well, but I would say it was more true during the PhD, and yeah, you need to prepare for that a little bit. Yes, I would say so. I mean, if you are doing some project and you really enjoy that, there's no harm in continuing in that project as well. But for me, I wanted to try what various things are there. So I also did one reading semester project on path integral formulation of QFT, but I didn't like it that much to spend a lot of time, so I continued with astronomy projects. But I would say it helps to have a broader understanding. So, like for example, if you attend seminars on various topics in astronomy, it helps to at least know somewhat what people are talking about. And you can get some insights from other fields as well. But there's no hard and fast rules. If you're working on one project and you really like it and you have a good rapport with your advisor, yeah, there's no harm in continuing with that project. What are my plans? So I've been currently applying for various postdoctoral fellowships right now this year, and I'm planning to graduate in this summer, but let's see how that goes. So I'm mostly applying for postdocs in the US and few places in Europe as well. But let's see how that goes. Right. Yes. So radio astronomy programming is definitely important whichever part of astronomy you're doing these days. So Python is used in a lot of areas of astronomy. I think Julia is getting more and more popular as well, but I've never used Julia. If you are doing more computationally expensive things, it may help to know C or Fortran as well. So this code I use Enzo, it's written primarily in C and Fortran. But for most of my research, I don't need to use C and Fortran to modify those, and I analyze the simulations mostly using Python. But if I want to change a specific part of the code to match it with my my work, I've had to use C for that reason. But it's always good to know programming, and it's not depending on what sort of project you are doing. You may well end up learning a lot while you are doing your first or second projects as well. So that was the case for me. So I had taken courses in programming at IISER, but I would say I learned a lot more when I did my first project in image processing and using Python. How relevant is R for astronomy? I don't know many people in astronomy who use R. So it's, from my experience, it seems to be more common with people who use statistics a lot, and it seems to be a lot more popular with ecologists, but I don't know. So, yeah. Scope of computational astrophysics. I would definitely say it is becoming more and more important, particularly as the computational resources are increasing, and also with next generation survey projects, for example, to make sense of what we see in those upcoming surveys. There are many ways where you need to generate mock catalogs to understand what sort of signals we expect. So I would say, yeah, there's a good future for the field of computational astrophysics to understand various objects. For example, we do not see the first stars yet. So in this area specifically, if we want to constrain what would be the properties of first stars, there are two ways. One way is to use all the physics we know and do as good simulations that we can to identify what their properties would be. And the second approach can also be what is called as near field cosmology. That is, you study extremely metal poor stars in Milky Way, and you observe their abundances of individual metals like silicon, oxygen, iron, etc. And based on their properties, you try to constrain the properties of first generation stars and their masses, etc. So yeah, it depends, but in many areas we do need to study computational astrophysics. For example, studying galactic dynamics is also one important area where there's a lot of computational work is being done.
Mihir, if you don't mind, you used a question by somebody, I guess. Aditya, I guess it was, who was asking about the density thing. Why do we like
Yeah, I was asking that question.
mass constraint instead of a density
Yeah,
constraint?
why don't we look at the density instead of the mass? Like, why do we look at the mass instead of density?
Right. So when you talk about density, what we need is gas density, and that it's a very good point. So if we want to study star formation, we need to look at densities, gas density, and gas temperature. But these are computationally expensive simulations. For example, the simulations I told you about, it's a relatively small box. It has very high resolution, and it took a lot of time. So you cannot do this for every sort of simulation. So it may be helpful to identify when and where population 3 stars form with the properties of the dark matter distribution, because it's a lot more computationally cheaper to do dark matter only simulation, and it traces the structure formation very well in the universe, as it's the main component of the matter in the universe. So if we have that, we can run dark matter only simulations, and in that scenario, we can, if we have some mechanism to connect where population 3 stars form to the properties of dark matter halos, then we can use those computationally inexpensive dark matter only simulations, which can have a much larger volume, and then we can use many semi-analytic models. For example, when first stars explode, they create metals, and how do these metals spread? And we can use some simple model for that, and these models are parametric, so we need to test various parameters, and we need to run various iterations of simulations. And for that, it's easier if we have a good model to link where population 3 stars form with their corresponding dark matter halo properties. So ideally, you are correct. We want to link it with to the properties of gas density and gas temperature, but it's not always feasible.
So like when we are even like looking at the mass, is there any volume constraint like do we when we are simulating, I exactly don't know how the simulation works, but when we are simulating, do we like keep a maximum value of like the volume around which you're the
Then,
areas around which the mass you're looking at, like, or is it
yeah,
just randomly spread mass?
no, that's a good question. So what we typically do is we start with a cosmological box of some size. So here, most of the simulations we did had box size of nearly 1 megaparsec, co-moving megaparsec, which means we are picking a representative 1 megaparsec patch of the universe, and we take our initial conditions from uh, power spectrum, from what we know from cosmic microwave background, etc. And we do simulations in only in that part of the universe. So we take that part, we assume it has periodic boundary conditions, that is, uh, rest of the universe looks just like that box that we are considering, and we only look at halos that are forming and gas densities that are increasing in that small part of the universe. But if we want to look at a more representative patch of the universe, we should simulate with a much larger box. But we cannot, if we have much larger box, we cannot go to high enough resolution that we need to study the formation of first stars accurately. So there is a trade-off here between how accurate simulations you can do and how good spatial resolution you have, and how representative your simulation box is. So yeah, the trade-off is you do some simulations with very high resolution and use insights from them to do the for the simulations which probe much larger cosmological volume.
Yeah, thanks. My doubt is clarified.
Yeah. What is my typical day like? So right now with COVID, I go to my office only a couple of days every week to my office, but I won't say it's anything particular. So I start in the morning, read archive, look for if there are any interesting papers, and depending on the time of month of the year. So for last few weeks, I've been busy with writing proposals. So I mean, I don't enjoy that part, but you need to write a lot. So that's one part of PhD. And depending on, sometimes it's just working on specific project or debugging a specific course. How useful has the IISER coursework been for you? I would say very useful. Uh, uh, yeah, I mean, like I did use some of the courses. For example, I took condensed matter physics course. I don't think I've used that, but I would say many of the statistical mechanics course, etc., I thought I won't use, but I've been using parts of that. Even like courses like atomic and molecular physics or quantum mechanics have been very useful. Even like concepts from classical mechanics and say action angle variables are used a lot in studying galactic dynamics. So I would say, yeah, I found them pretty useful. You won't use all of them for specific work you are doing. You may end up using some section of them more depending on what you are doing. Like if you're doing radio astronomy, maybe you would use more information from say electrostatics and electromagnetics courses and so on. But generally I would say, yeah, I found them pretty useful.
Okay, so if there are more questions, then feel free to ask them. I'll just stop the recording. People can still hang back and.
Yeah, if you have any questions at later point as well, feel free to email me at Mihir